Good afternoon, class. Lecture 14, Graph Slam Part 2. So last lecture, we covered Graph Slam Part 1, which focuses on back-end graph optimization theory. And today, we're going to cover this part. So we're going to start with an example, one-dimensional odometry optimization, and then we'll talk about some of the practical issues that arises when you start to apply this graph optimization for SLAM problems. All right. Right, example. So last time it was all math, theory, derivation. So probably you don't have a good feel of how it's applied, how it's implemented, and how it works. So here the intention is to provide you an example to get a better feel of how it's numerically solved. Okay. So this is a very simplified problem. 1D odometry optimization. So let's take a look. So please take a moment and read the problem. Okay. We have initial guess. X1 and X2. Odometry says X1 to X2 is 1 meter. And this is the motion model. And this is the measurement uncertainty. And the question is, find optimal pose of X2. Okay, so meaning that pose estimation problem. Okay. So this is a illustration of this problem. First, like we learned last lecture, we need to build graph structure. Okay. So we're going to define the node, which is X1 and X2. And X12 is the true position of X2 with respect to X1. And we have observation, measurement information. First, we need to start with error function. So that's that. E12 is Z12 minus capital 1, 2. And if we list everything out, then that's going to be Z12 minus parentheses X2 minus X1. Okay. Z12 was the measurement, which was 1. And then X1, X2 initial values were zeros. So we have 1, that's E12. And for linearization part, we need to compute Jacobian, which is del E1 over del X1 and del E12 over del X2. And if you compute that for this equation, then you will get X1 comma minus X2. Okay. Are you guys following? So take partial of E12 over with respect to X1 and X2. And if you plug numbers in, then you get that value. So this is what we got so far. And then we need to compute H and B now, where H is Jacobian transpose omega J, B equals to minus J transpose omega E12, where we computed E12 and we know J, we know information value or uncertainty. So we have everything to compute, right? So just plug numbers in. So here's Jacobian sort of covariance, let's say. And then Jacobian again, Jacobian omega E12. And if you just work that out, then you're going to get this matrix and vector, which is H and B, okay? So this is what we got so far. We have E12, we have Jacobian, we have H, we have B. Okay. Now let's compute. Let's compute del x. But before we do that, we need to remove the rank deficiency. Remember, so we need to remove the rank deficiency to actually compute, numerically compute. So we are going to fix x1. Okay, so that means delta x1 equals to 0. So x1 is not moving anywhere. So that's going to fix x. And if we can express that in matrix form, and that's going to be this equation. And what we are interested in here is this matrix. And we need to compute new H, sort of augmented Hessian, which is original H plus this. To make this solvable, okay? And we get this matrix, which is new H prime. And then let's solve for delta x, okay? Which is the direction and magnitude of where we should move in the next step for optimization process. So del x is H prime inverse times B. So we have everything to compute that, and that's 0, 1. So that means del x is 0, 1, meaning that during the optimization process, we should move the x2 value and add 1 to x2. So you add initial x plus del x, which is 0, 1. So this is the new x, okay? But this problem is simple enough that we don't have to iterate this, and this actually converges, and this is the solution, okay? And what this physically means is that x1 is 0 and x2 is 1, okay? But isn't that just adding odometry observation, which was z12 was 1, right? So if we just use motion model and let x2 equal to 1, because x1 was 0. But what if there is more measurements and the system becomes more complicated? The problem becomes more complicated. So in this case, there was no conflict between multiple measurements, right? So everything can be solved without compromising, meaning that without the information matrix in effect, deterministic approach can actually lead to this stochastic approach. Does that make sense? But when we when we have multiple measurements and the graph size becomes more larger, more complex, then obviously things will not be able to solve deterministically, meaning that things will start conflict, meaning that all the measurements doesn't point to the same direction. Are you guys following? So you have to compromise somewhere, meaning that you have to come up with some estimated value, optimized estimated value. And that's where uncertainty comes in, okay? And so in this case, we have three measurements. X1 to 2 is 1, X2 to 3 is 1, X1 to 3 is 3. Okay, so what does that mean? So X1 to 2 is 1, X2 to 3 is 1. So obviously, if we compute X1 to 3, then it should be 2, right? But the measurement says 3. So which is wrong? Who's the guy to blame? Who's wrong? Well, we're going to tackle this more systematically, meaning that it's not one measurement that's completely wrong, but every measurement has errors, uncertainties. So we're going to take that account. So sort of find the optimal value that compromises all measurements, considering the uncertainties. Okay, so that's basically what's going on here. And that's where these uncertainty comes in. Omega 1, 2, omega 2, 3, omega 1, 3. So, and what this says is omega 1, 3 is more reliable than omega 1, 2 or omega 2, 3. So we can put more weight on omega 1, 3 compared to omega 1, 2 or omega 2, 3. Does that make sense? So maybe omega 1, 3 was obtained by more accurate sensor or measurements, or scan matching or whatever. So it's more reliable, more accurate. So if you work this out, just like we did in the previous example, compute error, compute Jacobian, H, Hessian, B, and solve for del X, then this is what you get, okay? So what does that mean? X1 is 0, which is origin, right? We fixed that. And X1 is 1.25. X1, X2. X2 is 1.25, 1.25. X3 is 2.5. Okay. So that's what the solution is saying. And if you think about it, so Z13 was 3, but then the del X says it should be reduced, right? Instead of 3, there is a probably minus error based on other measurements. So it's decreased down to 2.5. And then if you look at Z12, which was 1, but considering this Z13, which was stating 3, so maybe you have an error for Z12, so it should be 1.25 instead of 1. And then Z23 will be 1.25, right? Not Z, X23 is 1.25. So it's X1, so optimized X here says X1 is 0, X2 is 1.25. So the delta is 1.25, and then X23 is 1.25. So X123 is 2.5. That's what the solution is saying. Okay. Does that make sense? All right. All right. So there was an example. Very, very extremely simple example. Okay. But in reality, it looks much more like this. Okay. So you're going to continue to collect data, sensory measurements, and you are going to travel around, and you're going to explore whether it's robot or a vehicle. You're going to explore different, new or old areas. And then you're going to collect measurements data, and you are going to create this graph that rapidly expands fast, and it's going to a huge graph structure. Okay, and the problem becomes computing this optimization problem becomes enormous. Okay, and solving it numerically becomes can be easily intractable. Okay, unless you are going to do a very small space exploration. Okay, but if you think about autonomous driving, it's definitely large scale problem. Okay, and many of the robotics problem does also experience this large scale problems. So in that case, how do we compute? So the problem here is that how do we inverse Hessian, right? Where Hessian is huge matrix. Okay. Well, luckily there are techniques. I don't know if you have been exposed to these factorization techniques in linear algebra. How many of you have heard of Cholesky factorization and QR factorization? Three? No one else? Okay. So if you have taken linear algebra that investigates deep into these numerical solver techniques, linear algebra, serious linear algebra courses does teach these test techniques, and there's a reason for it. Back then, you don't learn how it's used, but in engineering problems, and this is one example. Okay, I mean, same for me. I had no idea why am I learning this. I had no idea, but after 3-4 years, I realized that this is why I learned that course 3 years ago, but nobody told me why I need to study this. But I think there's so many things like this when you study undergrad introductory courses. Nobody tells you why you learn these courses. But anyway, so you can apply this factorization technique, and which allows you to solve this inverse problem very efficiently, fast. So we had to inverse this H matrix. But if we apply, the point is, if we apply this factorization theory, we can do it much more efficiently. For instance, if we use sparse-Cholesky factorization, we can convert H into R transpose R, and then we can solve for first. This is two-step process. We can solve for R R delta X equals R inverse transpose B, and then we can solve for del X R inverse transpose B. Okay. Why is this simpler, easier? Well, if you look into how the R matrix looks like, it's a triangular matrix. And if you have triangular matrix, solving this linear system is very convenient. It's easy to compute. For instance, if you have triangular matrix, so we are trying to compute del X, where D and R is given, then you need to solve for del X. So you're supposed to take inverse of R, right? R inverse, and we can solve that. When you solve this numerically, we can do it pretty easy. For instance, first row, we can solve for first row first, which is del X1, which is, so that is that term. So that is D minus 1 divided by R 1. And then you go to next row. Then you go to, you can solve for del X2, which is D2 minus R21 del X1, R22, but you computed del X1 in the prior row. So now you know del X1. So you can compute del X2. And then X3, you computed del X1, you computed del X2. So you know everything. So you can compute del X3. So you can, there's a chain, there is a series of equations that can be solved in chain. So there is no, this is very, easy to solve set of equations. Okay. And let's move on to the second approach, QR factorization. So in this case, we were Cholesky factorization does H to R transpose R. In this case, factorizing J equals to Q R0 matrix. And given that, let's plug those in to the equation. So the original equation was this, right? Where this was H and this was B, right? And now we have QR zeros, and we can put, we can plug those in, and this is what we get. But we can remove all of that, right? So we end up with this equation, right? And this is what we need to solve. And solving this is much easier now, because so now you need to inverse Q first, right? And inverse of orthogonal matrix, Q is orthogonal matrix. So inversing Q is simply Q transpose. So this is that. And then finally, del X, what we are interested in, would be R inverse Q transpose E ij. Okay. So transpose is simple operation, right? And R inverse, we talked about that, which is easy to compute. So we can solve for del X when we have large matrix computations. So that's one of the popular solver, numerical solver technique for inversing Hessian. And then let's move on to the next topic, which is hierarchical pose graph. So this is similar issue. So when the problem becomes large scale, then you will end up with many node and edges. And then do we have to solve all of that simultaneously at the same time with a single optimization problem? Well, the idea here is that maybe we can create a hierarchy. So we can solve for some of the key nodes and optimize that first, and then solve for local optimization problems separately in the next layer optimization problem. That way, large scale problem is decoupled into two layer. So that creates this hierarchy. Okay, so it's a hierarchical graph. So let's say we have a dense group of graph. The first thing you need to do is group the node of graph based on their local connectivity, and it'll be a good idea to use these node with multiple branches, multiple edges, meaning that it sort of means intersection areas where you have more relationships with more nodes. So that can be chosen as these representative high level nodes. And then you are going to apply so you're going to create this sparse graph. So meaning that you're going to neglect some of the low level local nodes and just focus on the high level key representative nodes and solve the optimization problem. And then you are going to and that's going to introduce you to how to correct reposition the node positions of the key nodes. And then you can after that, so this was the original node structure, key node structure, and then after optimization you are going to end up with something like this. And then you're going to handle the local nodes that is connected to these key nodes that was optimized higher level. That way you can solve for region local optimization problems separately. That way computation problem can be tangible, can be handled. Right. This well, this is supposed to be a graph, video clip that shows this approach. But for maybe I need to work on this next time. It's not playing on my iPad, so I'll have to skip. But you can type in on YouTube. You should be able to find this easy. Okay. All right. So actually, that's pretty much it for today. And I do have one more section, but I will leave that for you to take a look on your own. This is mostly extra information about what types of libraries that are available for developers, and some references, such as GTSim, G2O, Ceres Solver, and some example is provided for you, and how they actually coded the theory we learned today and last week. So please take a look if you would like to really understand how what we learned today during the lecture is actually implemented in code. Okay. And here's the references, and I would like to wrap up for today. And thanks for your attention. I will see you in the next lecture. Okay.